Well, hey everyone, and welcome back. Hopefully you recognize this image as a fault, specifically a normal fault occurring at a divergent plate boundary, hence these little arrows here. And you may be asking yourself, why are we talking about faults here? Isn't the video about folding? And that it is, and this is a very relevant point because faulting and folding are actually incredibly similar in that they are both deformational features of rock. So when we think of deformation that can occur to rock, we think of conditions, and one of the most clear ones for faulting is that it can be any sort of stress, whether that be shear, tensional, or compressional, meaning it can occur at any plate boundary, and also it has to be under very high pressure and low temperatures, right? Hopefully that's a review. Otherwise you can go watch a video on faulting. Maybe even watch my own if you feel like it. Right. But folding is different in that it occurs at high temperatures and high pressures. So folding, we need high temperatures in addition to the usual high pressures. And also, folding can only occur under compressional stress, meaning effectively it almost always occurs at convergent plate boundaries, as opposed to faults, which can occur at any plate boundaries. But with that out of the way, I'd like to give you a little metaphor. So under high temperatures, rock behaves differently in that it deforms more malleably. You know, under low temperatures, it would be like trying to compress a plastic ruler. It's not going to take much shape. You can see there's a bit of wiggle room, but if I try to push this much harder, then it's just going to snap. Meanwhile, under high temperatures, you'll get this more malleable behavior, which allows rock to behave sort of more like modeling clay, I guess, in that it'll take a different shape gradually in response to the higher amounts of pressure. There won't just be a sudden snap that releases a lot of energy. So to illustrate what I'm talking about, this is what a fold could look like. And this is most likely not at the surface because, as we know, it requires very high temperatures and the surface of the crust is quite cool. So here's a two-dimensional cross-sectional diagram, and we'll just label these A, B, C, D, and E, right? So the first thing you notice is that these have been folded such that they're pointing downwards, or these limbs you see are opening upwards. And that's all that a fold is, well, at least this type of fold, which is known as a synform. Syn as in synchronize, and form as in, I don't know, just form. And don't get that mixed up with syncline. There actually is a difference. A synform is not equal to a syncline. Remember that. A lot of people will use the terms interchangeably, but there is a slight difference. So just remember that. So that's a synform, but also under pressure, as you can imagine, the rock could also be pushed such that it points upwards and opens downwards. You know, it's like a reverse parabola, or a parabola that opens downwards. You know, it's like if you change the x in the function to a negative. Don't want to get too mathy here, but an anticline would look something like this. And we'll just label these again, A, B, C, D, and E. So an anticline points upwards and opens downwards. And you can tell I just made the mistake of using forms and clines interchangeably. It is an antiform, not an anticline. Even I use anticline and syncline interchangeably most of the time because they sound cooler, I guess. But it is an antiform. I'll get into the differences between forms and clines in a later video. But just to show you a more big picture, oftentimes anticlines and synclines, there I go again. I need to like keep track of how many times I mess up. Antiforms and synforms can be seen in similar, or actually within the same strata. Because if you think about it, oftentimes, it's like if you have a piece of paper and you're pushing it together, it's not going to deform such that it just stays like everything's pointed upwards or pointed downwards. If you crumple it, it's going to behave, it's going to be like, maybe a car would be a better representation of this. It's going to be folded upwards and downwards, and it's going to look almost like a wave to show where the energy's been distributed. So we can imagine this with strata as well. So if we've just got this cross-sectional diagram here, we'll have a layer on top called A. And then we can have something that just behaves, just drawing it at first, it looks like a sinusoidal wave, really. And then we can just draw our strata. There's a new one. And maybe there's a bit of one that shows up here. And then below it, just like that. And then we'll call this B, C, D, E, F, and G at the very bottom. So what's going on here? Well, since it was compressed over a very long distance, it wouldn't, just think about it, it wouldn't all just compress like everything goes upwards. There would be way too much, that'd be an incredibly uneven displacement overall. So we get some ups and some downs, effectively sort of balancing each other out, but you can still tell the deformation has occurred, which indicates to you that there has been a high amount of pressure put over this area. So we can just start labeling these pieces. This is an antiform, because currently the limbs are opening downwards and it's pointing upwards. Right here we observe a synform, another antiform right here, synform right there, antiform right here, synform right here, and antiform right here. And now hopefully this looks familiar. If you have any experience with waves in physics, really what we're just doing, antiforms correspond with the sort of crests we would observe on a wave here, and synforms correspond with the troughs. So if you want to just imagine this as one line, if you just sort of look at one of the lines that separates a strata, then you can look at it just in terms of increasing and decreasing, where are the crests and where are the troughs. And that's how you can identify them on larger pictures like these. As far as remembering which is which between antiform and synform, I don't have any real sophisticated method. My sort of go-to is just, this is what an antiform looks like. If you draw an A in there, it sort of fits. Meanwhile, with a synform, it doesn't fit. So, A for antiform, you could sort of draw it as an A if you drew a little line across there. Not very clever, very unsophisticated, but it gets the job done for me if ever I just, for some reason, am scratching my head. And one final thing, I want to talk about universal features to all folds. So it could be an antiform or a synform. So you've heard me use these terms. This is actually called the crest of an antiform, the uppermost point, while this is called the trough of the synform. We have this sort of, if we just draw a little line through here, that's our hinge line, like a door hinge, It is the line upon which the limbs hinge, which brings us to our next terms, the limbs, which can be found on either side. They are the pieces that dip either upwards or downwards, depending on whether it's an antiform or a synform. Those are limbs. Each one has a right limb and a left limb. And finally, there's a larger line that sort of goes through the hinge and the crest or the trough. And you'll hear it either called the axis or the axial plane. I prefer the term axial plane, simply because it reminds us that we're working in 3 dimensions here. The folds do stretch out, and you'll have something like that. Although we often represent them in 2D, they actually are 3-dimensional features. So the axial plane just reminds us that, hey, we are working in 3 dimensions here, and it just stretches out, following the direction of the fold, just going outwards from that crest or trough and the hinge. And that's all I really wanted to talk about. That was how folding occurs, high temperatures, high pressures, compressional stress, types of the basic types. There are many more, but antiforms and synforms, the most simple kinds, and some universal features to all folds. I'll be doing more videos on these just because there is a lot to talk about, but hopefully this basics video was informative. Otherwise, good review. Hopefully you guys enjoyed, and I'll see you all in the next video. Ciao.